Hey everybody, just wanted to wrap up our unit on circular motion with a quick talk about universal gravity and how it's related to circular motion. We didn't get a whole lot of time to cover that in class. I know you guys read about it, but I wanted to just give a brief lecture on that. So the idea of universal gravity is that Newton discovered this relationship, and if we have um, a couple pieces of masses that are separated by some distance, um, we recognize that there is an attractive force that can be seen on these two objects, and we call that attractive force gravity. So, force object 2 exerts a force on object 1. There's also a equal and opposite force of object 1 on object 2. That's a Newton's third law pair. So these objects are attracted to each other. It's true of any two pieces of mass. The force is actually pretty small, but as we get a lot of mass, like in a sun or a planet, then obviously the force can be grow to be very large. So the size of the force, if we just pick, say, one of these forces and we want to describe it, the size of the force depends on a couple things. It's The size of the force is proportional to how big the body is that's attracting it. So it grows with the size of the object that's attracting it. It also gets bigger depending on the mass that that the body that is getting attracted is, and it goes down by the square of the distance. And we always measure the distance as the distance from the center of that mass. Um, uh, Now that's just the proportional relationship. So if I wanted to make a statement, however, about what the size of the force is, I need to actually set the size of the force to some value. So if I want it to be equal to something, I have to know what the proportionality is. So there is a constant that sits out in front of here that sets the size of the force. So over here on this side of the equation, we have mass in kilograms. We have another mass in kilograms, and we have meters squared in the denominator. And over here we have newtons on this side of the equation. So if I'm just doing a dimensional analysis, G has to have units that is going to get me from kilograms squared per meter squared to newtons. So I'm going to need newtons on the top. I'm going to need meter squared on the top to cancel with the meter squared on the bottom. I'm going to need kilograms squared on the bottom to cancel with the kilogram squared on the top. And then it's going to have a certain size that describes how big the force is when I have m1 equal to a kilogram, m2 equal to a kilogram, and the radius equal to 1 meter. And that's the size of the force. So imagine two 1 kilogram objects that are separated by a meter. This is the size of the force in newtons. It's a very small force. Obviously, you can see it's 10 to the minus 11th. It's hard to measure unless you have really large, massive objects, obviously like the Earth or the Sun. So let's just think about how that force changes when you vary any of those parameters. Well, like I said, the force is proportional to the masses. So let's just do an example problem. Let's say I have m1, m2, and the force on them is, let's say F. The gravitational force is F with M1 and M2 at some R. Okay. Now let's say we double M1 and we double the distance between them. How does the force change? So we can use this factor of change analysis tool that we have. So the factor of change analysis says that we start with a force. That we know the relationship. It's G M2 M1 over R squared. And then for everything that doesn't change, you plug in a 1. And for everything that does change, you plug in the factor of the change. So G doesn't change, so I'd plug in 1 for that. M2 doesn't change, so I'll plug in a 1 for that. M1 doubles, so I'll plug in a 2 for that. And the radius doubles, so I'll plug in a 2 for that, and that's a 2 squared. So if I work that out, I got a 2 over a 2 squared, that's a 1/2. So this represents the factor of change for the force. So if I start with some force from M1, M2, and R, and then I double M1 and I double R, I will see the force be cut in half. So if we remember, this was this factor of change method to determine what that new force is relative to the previous force. So if I double M1, I double R, then the new force is 1/2 of the old force. Okay, so how does that then affect? How do we then use that to apply that to circular motion and gravity? Well, for these massive objects, actually before I go to that, let's actually apply this to somebody on the surface of the Earth. So let's imagine we've got the Earth here. It's got some known mass and it's got some known radius. And up here on the North Pole, let's say, is a person standing there. And we've examined people on the surface of the Earth before, and what we know is that the force of the Earth on that person is equal to G times the mass of the person. So we know that to be true, that G is 9.8 newtons per kilogram. But we also now know a more general expression. We know that the force of the Earth on the person is also going to be equal to G times, well, let's see, we got the two masses. One is the mass of the Earth, the other is the mass of the person, and they're separated by a distance of the radius of the Earth, because we're always measuring from the center of the mass, and that person is a distance of RE, or the radius of the Earth, away. So the radius of the Earth squared goes on the bottom. Well, what does that say? Well, these two expressions are both true. So what does that mean? Well, that means that all of this part right here must be equal to G. So G, which equals 9.8 newtons per meter, must also be equal to G times the mass of the Earth over the radius of the Earth squared. If you go look up on Wikipedia what the numbers are for the mass and the radius of the Earth, and you plug them in, you'll find that you'll get exactly 9.8 newtons per meter. Okay, so now let's go ahead and apply this to a planet that's circling the sun. So if we look at a sun with a planet that's circling around it in circular motion, that's moving at a velocity that is at some radius away. We know that the sun has some mass, we know that the planet has some mass, and let's draw a force diagram for that. So let's take a side view. So here's our sun that's at the center. Here is our planet. And there's one and only one force acting on it. It is the force of the sun on the planet. It's a gravitational force. So now we can apply Newton's second law. Some of the forces in the radial dimension have to be equal to the mass of the planet. That's the thing that that's our system, times the radial acceleration. Well, what is the force on the planet? Well, it's one and only force that is acting on it. And we know that if it's in circular motion, constant velocity, that our radial acceleration has to be v squared over r. There's another way to describe it. As we learned, it's 4 pi squared r over t squared. That's the other way to describe it. But now we can express the left side of this equation. We know an expression for how big the force of the sun is on that planet. The force of the sun on the planet is this universal law of gravity. It's g, the mass of the sun, times the mass of the planet, over that radius, that distance between them, squared. And the right side of our equation stays the same. And there you go. There's an expression that relates the mass of the sun, the radius, and the speed that the planet is moving around it. Obviously, there's another way to express it. This one actually might be a little more intuitive because we quite often talk about the amount of time that a planet takes to go around the sun. For the Earth, that period is 1 year. So to express it maybe this way might be a little more instructive. So let's go ahead and use that expression. Let me just kind of put this together. We can make a few more observations. So one observation is simply that I get some things to cancel and to combine together. The mass of the planets cancel out. I could collect my r's together over here. And what am I left with? I am left with, I'll move the t squared to the other side. So g, mass of the sun, t squared, is equal to 4 pi squared r cubed. And if you notice, this is Kepler's third law. Kepler's third law was simply that the square of the planet's period was proportional to the radius cubed. And that's exactly what that expression says. And where do we get that from? We simply got that by starting with Newton's second law for radial motion, for circular motion, recognizing that the radial acceleration has to be equal to v squared over r, and that the one and only force is generated by the universal law of gravity. Okay, that's it.